Good morning, guys. So today we're going to pick up where we left off last time. A little bit of curve sketching, section 4.3, all that good stuff. We're also going to talk a bit about L'Hopital's rule today, I think. So I guess I'll have to give a few more minutes for some other folks to show up. That link has only been up for about 3 minutes now. But yeah, that's the plan. So I'm gonna get some fresh paper over here. The .cam software fired up and connected.
Mr. B, I have a question.
Sure, what's up?
So I was doing one of the homeworks and I was watching the lecture on the video, and I was wondering if we could talk about it because I kind of did it mechanically. I don't really understand what I was doing.
Sure. Yeah. What was the problem you were working on?
It was question 11 on the homework 9.
Okay.
It was the part where they were getting the signs to be positive and negative. I couldn't understand how they got that.
And you said it was question number 11, right?
Yes, sir.
Okay. Yeah, it couldn't hurt to take a look at a problem or two at the start here. Sorry, question 11. Okay. So there are some things here we haven't talked about yet. Namely, we haven't talked about concavity or inflection points yet. So that's something that we still need to discuss. Maybe this would be a good problem for me to introduce those ideas. When you say you're having a hard time figuring out how they got the sign, you mean like where f prime is positive and where f prime is negative?
Yeah.
Okay. Okay. Let me do one thing. So I'm going to introduce this idea of concavity and an inflection point. And then I will come back and use this as my first example. Does that sound okay?
Yes, sir. Thank you so much.
Yeah, of course, of course. Looks like we got pretty much everybody here now. So I'll go ahead and jump in. All right. So, of course, this is Calc 1. Today is today. Last time we talked a little bit about, Last time we talked a little bit about increasing and decreasing functions, as well as the mean value theorem. The mean value theorem isn't something that we're going to use a whole lot in this class, but if you go on to take any more theory-based math classes, the mean value theorem is a hugely important tool for proving other theorems. That's really why we cover it here. And also, it's a good way for you to start thinking about what it means for a function to be smooth and the idea of nice smooth transitions from one slope to the next. But today, we're going to spend more time on 4.3. And we might talk a little bit of L'Hopital's rule. But I'm thinking probably because of the way I set up the homework here, where did we go? L'Hopital's rule we talked about a little bit. Yeah, okay, so that'll be all. There is one more major concept from section 4.3 that we need to talk about. And that's something that Aubrey was just asking about, I think, or at least is relevant to the problem that she was asking about. So let's jump back into that really fast. So section 4.3 revisited. Remember, this is on how derivatives affect the shape of the graph. And we need to talk a little bit about higher derivatives. So we've only mentioned higher derivatives once or twice in this class because they're not super relevant, but back when we were talking about the derivative as a function, we talked a little bit about velocity and acceleration as they relate to position. Acceleration is the second derivative of your position. So velocity, so let's say recall, if f of t, I'll use the normal notation, s of t is the position of an object moving in a straight line, then v of t, which is the derivative of s, is called the velocity. And it's the rate of change. So it's the velocity of that object at time t. And it is the rate of change or slope of s of t. A of t is the derivative of the velocity function, which means that's the second derivative of the position function. This is called the acceleration of the object. What I would like to do, if v of t is the velocity or the rate of change, and we can identify that with the slope of the original function, I would like to try and identify a of t with some other geometric feature of the graph of the original. And I think if we draw a couple pictures, you will be able to imagine what I'm saying. So I'm going to draw two graphs of s of t. In this first picture, my position starts out down here at 0, and as time increases, so this is my t-axis, my position is getting larger and larger. So my object is moving forwards. My slopes here are all positive. And that makes sense because this is an increasing function. We can see that. My slopes here are also all positive. So the question I'd like to ask you guys is, what's fundamentally different about these two functions? They're both increasing, right? But why is this one shaped differently than this one? And how could we phrase that in terms of the velocity and acceleration? Here, in this first function, I am my velocities are all positive, right? Right here, the slope of this guy is positive. And remember the slope of the tangent line, that is the derivative. Here, this guy also positive. So s is everywhere increasing, but the velocity, while always positive, is decreasing. So I should say s of t is increasing, but the velocity is decreasing. And in this guy, s of t is still increasing, right? The original function is increasing. But something else is happening. Here my tangent lines start off kind of shallow, and they're getting steeper and steeper. So also the velocity is increasing. So two different increasing functions. However, in the one guy, you have this kind of concave down shape, if you're familiar with that word concave. And over here, you have this kind of concave up shape. Some people call this convex and call this concave, but in Calc 1, we call this concave down, and we call this concave up. The big difference here is that in this guy, even though s of t is increasing, the velocity v of t is decreasing. Because as you look further and further out, these tangent lines are getting shallower and shallower. They start off steep. So here maybe the velocity is like 2. Here maybe the velocity is like 1. Here maybe the velocity is like 1/2. So s is increasing, but v is decreasing. So the original function is increasing, but the derivative is decreasing. Here, s is increasing, and if you look at v, maybe here v is like 1/2, here v is 1, here v is like 2. S is increasing and v is increasing. If you think about this as being like a car accelerating down a straight road, then what's happening here is I start with my foot on the gas quite hard, and then I'm letting my foot off the gas. In fact, I've let my foot all the way off the gas and I may be hitting the brake. So I start off going quite quickly, but then I'm slowing down. Here I start off going quite slowly, but I'm speeding up. In both cases, the car is moving down the street, so s is increasing. But in the one case, the velocity is getting smaller, so I'm hitting the brake. I'm already moving here, and I'm hitting the brake, so I start to slow down. Here, I'm starting off going very slow, and I'm standing on the gas to go faster and faster. The rate of change of your first derivative is information that you can get from your second derivative. So here I'm hitting the brakes. Here I'm standing on the gas or hitting the gas. In other words, in this guy, my acceleration is positive. My second derivative is positive because my first derivative is increasing. So that means your acceleration is positive. In other words, I'm hitting the gas. Here, my velocity is decreasing. My first derivative is decreasing, which means my second derivative, a of t, is negative. I'm hitting the brakes. So this kind of shape difference, even though both functions are increasing, the graphs have different shapes. That's the sort of thing that we're talking about here in section 4.3, can be tested for by doing the same thing with the second derivative that we were doing with the first derivative in the last class. So I'm going to give you a couple of definitions and a theorem, and then we're going to look at an example. We're going to look at number 11 from homework 9. So first definition, we say f of x is concave up on the interval AB if f double prime of x is positive for all x in AB. We say f of x is concave down. And these are the things we're defining, concave up and concave down. If f prime prime x is negative for all x in AB. And there's 4 possible combinations. You can be increasing concave down, increasing concave up, decreasing concave down, and decreasing concave up. So I want to draw a little bit each of these. Increasing concave down. Increasing concave up. Those are the 2 pictures that we had on the previous page. And then there's decreasing concave down. So that looks like this. And then there's decreasing concave up, which looks like, I think, yeah, this. The way I like to think of it is if you poured water on top of the graph of a concave down function, the water would all run off of it, right? So the water, and if you poured water on the graph of a concave up function, then the water would kind of pool, it would want to collect. There's a nice theorem attached to these ideas. Well, maybe I'll save the theorem. I'll save the theorem. So let's go ahead and take a look at that example problem number 11 from homework 9. And then I'll share with you the theorem about local extrema, because really there's 2 theorems and they're connected. So do we have a reasonable feeling for why these are concave down? If you look at the slopes of the tangent lines, they're getting shallower and shallower. Right? Or the slopes of the tangent lines here are getting steeper and steeper. But the idea is that the velocity, or the first derivative, is decreasing. Here, this tangent line is large positive slope, small positive slope, so the tangent line's slope has gotten smaller. And here, this tangent line is small negative slope, large negative slope, so it's still getting smaller. And over here, the tangent lines are getting steeper and steeper, so the velocity, or the first derivative, is increasing. And again here, the velocity or first derivative is increasing. Starts off very negative, and then over here it's still negative, but much less negative. Here, the tangent lines have to have negative slope. The first derivative has to be negative because we're decreasing. All right, remember, decreasing means f prime is negative, but it's concave up, so f double prime is positive. Here we're increasing, so f prime is positive, and you see all the tangent lines have positive slopes. And the tangent line slopes are getting larger, so f double prime is positive. Here increasing, so f prime is positive. And yep, all of these tangent lines have positive slopes. But we're concave down, so f double prime is negative. Let me zoom in a little bit more so those double primes are visible.
I have a question.
Sure.
The 4th graph doesn't really look like what you said about holding the water. So I still am confused about how that would be concave up.
Well, so because I wanted this to be both increasing and concave up, I don't have like the other side of a bowl here. But imagine you connected a piece that looks like this to a piece that looks like this. So down here, I'll fill in a little bit more example stuff. This guy is concave up everywhere. So if you poured some water in here, this would hold water, right? I can't use him as an example for one of these four things because he's decreasing over here. And he's increasing over here. So I wanted to separate the four behaviors in the last one. But he's everywhere concave up. And that's what I mean by he would like hold water. And if you flipped him upside down, then water would run off the back. And that would be concave down. Now, a point where concavity changes is called an inflection point.
Excuse me, sir.
Yes.
Yeah, the fourth graph where you say decreasing concave up. So can you explain me how the acceleration is greater than 0?
Yeah, sure. So right here, my tangent line is very negative, right? Right here, the tangent line has slope like -10. Over here, the tangent line still has negative slope, but it's not as negative. So here, f primed is maybe -10. Here, f primed is maybe -1. And -1 is bigger than -10. So f primed is increasing, which means f double primed has to be positive. So remember, concave up means as you go from left to right, the slopes of the tangent lines are increasing.
Okay, thank you.
It's a little bit counterintuitive. I always have to think just for a second before I draw that one, because I have to go, oh, how can I be decreasing but also concave up? And just remember that if you're going from really, really negative to less negative, that's still an increase. So even though these tangent lines both have negative slopes, the slope here is greater than the slope here, because -10 is smaller than like -1.
All right, thank you.
Any other questions on the definition of concave up and concave down?
Can you repeat one of the last sentences you said where you said concave up has the slope of tangent lines, blah, blah, blah?
So here, this piece is concave up, because
Right.
as we go from left to right, the slope of the tangent lines is increasing. Here, maybe the slope of the tangent line is like -10. Here, the slope of the tangent line is maybe -1. So -1 is bigger than -10, right? It's
Yeah,
right
right.
of that on the number line. So as we go from left to right, the tangent line slopes are getting larger, which means f primed is increasing. So f double primed, the derivative of f primed, should be positive. That makes sense?
Yeah, get larger from left to right.
Yep. Yeah. So remember,
Oh yeah, now I see it. Okay, cool.
any function is said to be increasing if its derivative is positive. So here, f primed is increasing, which means its derivative, which is f double primed, is positive. It's kind of sneaky. So let's see if we can make this a little bit more concrete with an example. This is what I mean by holding water, right? And then let me write down, we need one more definition and then we can look at that problem from homework 9. So the last little definition we need here is the definition of an inflection point. So point on the graph of f of x at which the concavity changes either from concave down to concave up, or vice versa. So an inflection point right here is an inflection point. Because if you look over here, the graph is concave down. If you look over here, the graph is concave up. And this point right here is an inflection point, because that is a point where the concavity changes. Okay, so let's look at this example problem from the homework. This is number 11 from homework 9. It says let f of x be x cubed minus 9x squared minus 21x plus 8. And we want to find intervals of increase and decrease local mins, local maxes, inflection points, and intervals of concave up, concave down. Okay, so we want to find all these things. To find intervals of increase and decrease and local mins and maxes, we need the first derivative. So I calculate f prime. And f primed here I can get with the power rule. So x cubed, he differentiates to 3x squared, minus 9x squared differentiates to minus 18x, and minus 21x differentiates to minus 21. The 8 differentiates to 0. So this is f prime. If I want to find intervals of increase and decrease, or local mins and maxes, I need my critical numbers. So I'm going to factor f prime. First I'll factor out the common factor of 3. And I'll be left with x squared minus 6x minus 7. And then I have to see if that quadratic factors nicely. So I need two numbers that multiply to -7 and sum to -6. That'll be -7 and +1. So this is 3 times x minus 7 times x plus 1. So my critical numbers for f are places where f primed is either 0 or undefined. F primed is a polynomial. He's never undefined, but he's definitely equal to 0 when x is equal to 7 or -1. So now I'm going to make my little number line. I did post, let me show you here really quickly, in our modules on Canvas, I think I put it under the review material section. Yeah, a thing on solving polynomial inequalities. So here's Paul's online notes where he shows you how to solve inequalities like these. And he does it all with test points. And I think he discusses the multiplicity trick a little bit here. But this is the game. So if you're having a hard time following what I'm doing with these number lines, come check out this Paul's online notes thing. There's also one on rational inequalities, which is the same skill, just for slightly more complicated functions. So I don't really want to spend a whole lot of time going back over how to do that stuff. I'm just going to do it here, but I will do it slowly. So if it's something you haven't seen in a while, we can talk about it a bit. On my number line, I plot anywhere f primed is capable of changing sign. I plot any of the critical numbers. In pre-calculus, if you took pre-calc with me when we were just solving inequalities, I called these important numbers. But now, because we're talking about the relationship between f and f prime, the word critical numbers is useful. So this splits the number line up into 3 regions. F is either increasing or decreasing everywhere over here, because f primed is either positive or negative everywhere over there. It's not capable of changing sign anywhere in this blue box region because he's only capable of changing sign at these numbers. Similarly, everywhere in this region, f is either increasing or decreasing. Everywhere in this region, f is either increasing or decreasing. To figure out which is which, I can test a point from each region. So over here, I could test x equals -2. If I plug -2 into f primed, that's 3 times -9 times -1. This is 3 times +9, which is +27. So f primed is positive over here, which means f is increasing everywhere over there. In this middle region, I could test x equals 0. F primed of 0 is 3 times -7 times +1, which is -21. So f primed is negative everywhere in that region. And over here, I could test x equals 8. So f primed of 8 is 3 times 1 times 9, which is +27. So f primed is positive here. And the truth is that once I knew any one of these regions, I could have gotten all the others using that multiplicity trick. So if you remember the multiplicity trick, the rule is fairly simple. If the number on the number line comes from a factor that has an odd multiplicity, then you will change sign as you jump over that number. So I could have just tested x equals 0 in the middle, found him to be negative, And then immediately I would know that this region is positive and this region is positive because both of those numbers came from odd multiplicity factors. If you don't remember the multiplicity trick, you can always do exactly what I did here. Just test one number from each of those regions. What this means is that f is increasing on the intervals -∞ to -1 and 7 to infinity, because f primed is positive there. And f is decreasing on the interval -1 to 7. So that's the first part done. We found the intervals of increase and decrease. This is called the first derivative test. And not only does it tell us where the function is increasing and decreasing, it also tells us what happened here at -1 and what happened here at 7. If f goes from increasing to decreasing at -1, I want you to imagine what happens at -1. So at x equals -1, f of x goes from increasing to decreasing. What does that look like? That looks like this: increasing, 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 decreasing, decreasing, decreasing. So this right here had to have been a local max. And the max value is f of -1, which we find by plugging -1 into the original. Let's see if I can get that on the page here. Yeah, so that would be -1 cubed minus 9 times -1 squared minus 21 times -1 plus 8, which is -1 minus 9 plus 21 plus 8. So that's -10 plus 29. That's positive 19. So the max value is 19. And we have a local max at x equals -1. This is called the first derivative test.
Actually, sir, can I take the picture of the top?
Sure.
That's no, go a little bit up where you make a graph.
Like this?
No, up. You make a graph. Okay, that one. Okay.
So which piece did we want to go on? This graph here? Or the graph
Yeah,
down?
this graph here, yeah. Before homework 11, yeah, the whole, okay.
Okay, there we go.
All right, thank you. Got it.
No problem. So we found the intervals of increase and decrease, and we found a local max at -1. We still have to figure out what happened at 7. At x equals 7, f of x goes from decreasing, because f primed is negative here, to increasing. Therefore, so what does that mean? That means we're decreasing, 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 turnaround, increasing, increasing, increasing. So that means this point had to have been a local min. So therefore, f of x has a local min at x equals 7. And the min value is f of 7, which is 7 cubed minus 9 times 7 squared minus 21 times 7 plus 8. And my arithmetic is not very good, so I'm going to employ some help here. Oh, no, not that. So we need 7 cubed minus 9 times 7 squared minus 21 times 7 plus 8. That's negative 237. So these are the minima and maxima. And we get all of this stuff, the intervals of increase and decrease and the mins and maxes, from this number line, from the number line for f primed. To figure out points of inflection and concavity, we do the same thing. We build a number line just like this for f double primed. Because remember, if f double primed is negative, then my function is concave down. If f double primed is positive, then my function is concave up. I would like to draw your attention to something here, and that's this. If I have a local max, like I do here at x equals -1, then my function is concave down, or at least most likely is concave down. In other words, if f double prime exists here, then f double prime has to be negative. And if f double prime exists here, then f double prime has to be positive. So that's called the second derivative test, and I'll explain exactly what that is a little bit down the road. First, let's finish solving the problem. So we want to find inflection points and intervals of concave up and concave down. I use f double prime. So I'm going to take f primed and differentiate it to get f double primed. The derivative of 3x squared is 6x. The derivative of -18x is -18, and the derivative of -21 is 0. And here I could factor out a 6 if I wanted, and I get 6 times x minus 3. So I make my number line for f double primed. I put on it the only places where f double prime can change sign, and I test a point. Over here, I could test x equals 0. And when I do that, f double primed of 0 is -18. In particular, it is negative. Over here, I could test x equals 4. F double primed of 4 is 24 minus 18 is 6, it's positive. So f of x is concave down on the interval -∞ to 3, that's this region, and f of x is concave up on the interval (3 to infinity). All right. And then my last thing is just to identify the inflection points, if there are any. So is there an inflection point here? Is there anywhere f goes from being concave down to concave up or vice versa? Yeah, right here at 3. Right? I'm concave down to the left of 3. I'm concave up to the right of 3. So x equals 3 has to be the location of an inflection point. Now, inflection points are points, so we should say what exactly the point is, i.e. the point. I need to figure out what f of 3 is. 3 comma f of 3. And I might get lazy here again. So f of 3 is -109. So this is the point 3 comma -109. And that's it. That's the whole game here. So we found intervals of increase and decrease. We used that to find local mins and maxes. And then we found intervals of concave up, concave down. And we used that to find inflection points. There is quite a lot of work here. I'm not going to pretend like this is short. It's not. Let's see. I don't think I can arrange it all to fit. Yes.
So the inflection point, it is only when now we have a top prime. So with a 1 prime, we cannot get the inflection point?
Correct. Yeah, you cannot
Okay.
find inflection points from f prime. You need f double prime to find inflection points. So let's go through this one bit at a time. Are there any questions on the calculation or factoring of f primed or how I found the critical numbers? Any questions about this step?
No, but I have a question about f double prime.
Okay, we'll get to that in just 1 second. Are there any questions about how we cooked up this number line or how I was able to assign the plus, minus, plus here? So really what we're doing when we do this is we're solving 2 inequalities at once. We're solving the inequality f primed is greater than 0. We found f primed is greater than 0 on -infinity, -1, unioned with 7 to infinity. And f primed is less than 0 on -1 to 7. That's really what we're able to do, or what we're doing with that number line. And then we concluded that because f primed is positive here, f is increasing there. And because f primed is negative there, f is decreasing there. Then we came to this stuff, I'll leave that there. Then we came to this stuff for the local mins and maxes. These critical numbers where f prime changes sign are places where f goes from increasing to decreasing or from decreasing to increasing. So those had to be local maxes and local mins. So this local max here was at the point -1, 19. And this local min was at the point 7, -237. And we found those by taking these guys from the number line, the critical numbers, checking whether it's a min or a max based on whether f went from increasing to decreasing or decreasing to increasing, and then plugging those x values into the original function to find the point on the graph.
Let's say there was like another decreasing. Would you put like another local min?
If over here, like to the right of 7, there was another decreasing, then so suppose at x equals 10, f prime went from positive to negative. That would be another place where f goes from increasing to decreasing. So that would be another local max.
A local max, got it.
Yeah, if over here we had negative, like maybe from negative infinity to -5, f prime was negative, then -5 would be a place where we went from decreasing to increasing. So that would be another local min.
Got you, thank you.
And then the inflection points come from f double prime. So I think there was a question here, right? Something about the second derivative?
Yeah, I'm just, so I kind of get an idea of what f prime does, but I don't really get double prime, like what it does in a graph picture.
So that's kind of what we're introducing today. This is new material for us. F double prime tells us about concavity. F double prime tells us whether f primed is increasing or decreasing. If f primed is increasing, then our graph is concave up. And if f primed is decreasing, then our graph is concave down. F prime being increasing means f double prime is positive. So over here in the interval 3 to infinity, there's two ways we can discuss this. This means f prime is increasing on 3 to infinity, which implies f is concave up, and f prime being negative over here, sorry, f double prime being negative over here means that f primed is decreasing on that interval, which is negative infinity to 3. And that implies f is concave down. So there's two ways to think about what f double prime tells us about the graph. If f double primed is positive, then f primed is increasing because f double prime is the derivative of f prime. And if your derivative is positive, then you are increasing. So f double prime being positive means f prime is increasing. But f prime increasing means f is concave up. So you kind of have to chase it back through two layers. If f double primed is negative, like it is here, that means f primed is decreasing, which means f itself is concave down. So let's look at the graph of this function. I'm going to take this original and throw him into Desmos, and we can identify all of these interesting points.
That last f of 3, did you plug that into the original equation?
Yes.
Okay, cool. Thank you.
Yeah, where was that? Here, right? So if I want to find the inflection point associated with x equals 3, that's going to be the point on the graph of the original function where x is equal to 3. And that is, yeah, this guy. So I put him into the original, and then I did the calculation with the calculator. So I'm lazy. So let's come back here. X cubed. What else do we have? Minus 9x squared minus 21x plus 8. Now the scale is going to be a little bit weird. We know these y values are pretty out of control. So let me move my y scale to something like, what do we have? What was the largest one? Negative 237. So let's go negative 250. Yeah, that looks good. All right, here we go. So local mins, local maxes, where did we find those? Local min at x equals 7, local max at x equals -1. So -1 comma f of -1. This is the local max at x equals -1. Then we also had a local min at x equals 7. So 7 comma f of 7, that's the point on the graph of f of x when x is equal to 7. This was a local min at x equals 7. And you see everywhere to the left of this guy, we're increasing, increasing, increasing. And then at this point, we turn around and we're decreasing, decreasing, decreasing. So anywhere you go from increasing to decreasing has to be a local max. And anywhere you go from decreasing to increasing has to be a local min. The inflection point, if you look at this piece, if I were to just zoom in and pay attention to this piece right here, that's concave down. Water, if you poured some water over the top of this, all that water would run off. And if I zoom in and look just at this piece, this is concave up, because if I poured some water in here, it would all pool. So somewhere in between those two, we switched from being concave down over here to concave up over here. And the point where we switched looks to me to be somewhere right around here. Now, where was it exactly? I think it was 3. This is our inflection point. Where we went from concave down to concave up. To the left of the IP, the inflection point, we're concave down. To the right of the IP, we're concave up. And you can see how if you have all this information, you can draw a pretty nice graph. Cool stuff, right? Krishna asked, do we need to know this graph? The idea is not that I expect you to know how to graph this already. The idea is that I'm teaching you how to graph this right now. If you can find these x-intercepts, you can find the mins and the maxes, you can find the inflection points, and you know the end behavior, then you can draw a really awesome graph. So while I don't expect you to know how to graph this yet, I am expecting you to be learning how to get this graph right now. That's the purpose of 4.3 and 4.5, is to teach you how to draw really good graphs using the information from the first and second derivatives. Okay. So that was a really nice example problem, and a lot of your homework looks like that, right? There's a lot of stuff like this in your homework where you're finding intervals of increase and decrease. At first, you're going to do it from graphs, but then eventually there's a lot of stuff just like this where you have to use calculus to find intervals of increase and decrease. So I want to talk to you about 1 or 2 more little theorems, and then we're going to work some more examples, talk maybe a little bit about L'Hopital's rule. I might save L'Hopital's rule for Friday, because I want to make sure that you get a good taste of this graphing stuff. So here's something that we've stated, but never written down carefully, and I want to make sure it gets into your notes. This is called the first derivative test. It says if f of x is differentiable and f primed of x changes sign at x equals c, then if f prime goes from negative to positive at x equals c, the point c comma f of c is a local min for f of x. Why? Because f primed went from negative to positive. That means f went from decreasing to increasing. And also, if f primed goes from positive to negative, oh, I wrote 3, sorry, this should be x equals c. Positive to negative at x equals c, then c comma f of c is a local max. Hamlet, no. Local max for f of x. Sorry, my dog over there looking at himself. So this is called the first derivative test, and it's what we're doing with that number line. The logic here is very straightforward. If f prime goes from negative to positive, that means f goes from decreasing to increasing. If the only way to go from decreasing to increasing is to roll through a little valley. And those little valleys we know are all local mins. If f prime goes from positive to negative, that means we're going from increasing to decreasing. And the only way for that to happen is if you roll through a little hill. Those little hills are all local maxes. There's another way to state this. If f of x is twice differentiable, at x equals c, i.e. f double prime of c exists, and f prime of c is 0 or undefined. Actually, really just if f double prime is 0, yeah, we don't have to worry about the other one. Then f prime prime of c being positive implies c comma f of c is a local min. And f prime prime of c being negative implies that c comma f of c is a local max. And I want to think about why. So this second guy here, sorry, is called the second derivative test. That's the name of this other theorem. So first derivative test, second derivative test. Both of these are tools for recognizing what's happening at a critical number. If f double primed is positive at c, in other words, f double primed of c is positive, that means f of x is concave up at c. So if you're concave up and you have a critical number, then that critical number has to be a local min. If you're concave down, if f double primed is negative at a critical number, then that critical number has to be a local max. Right? So if f primed is 0, that means the tangent line there is horizontal. And if you have a horizontal tangent line and you are concave up, then that's got to be a local min. And the way to check to be concave up is if f double prime is positive. If you have a horizontal tangent line and you are concave down, then that's got to be a local max. So if f double primed of c exists and f primed of c is 0, the f primed of c equals 0. This means horizontal tangent line. So if f primed of c is 0 and f double primed is positive, then you have a horizontal tangent line and you're concave up. That means you got to be a local min. If you have a horizontal tangent line and you are concave down, that means you got to be at a local max. So you have a bunch of questions in your homework that ask you sort of in an abstract setting where I don't give you a formula for the function, so you can't do the number line thing. Just if f primed is this and f double primed is this, what's going on at that point? I'd like to take a look at 1 or 2 examples like that. And I might as well pull them from your homework. I don't see any harm in that. So let's look. Here we go. Suppose f double prime is continuous everywhere. So f double prime exists. If f primed of -1 is 0 and f double primed of -1 is 7, what can you say about f? All right, so let me copy this down. This is homework 9, number 16. If f primed of -1 equals 0 and f prime prime of -1 is -7, what can be said about f of x? So let's look at these two things together. Let's look at our second derivative test together with this statement. If f primed of -1 is 0 and f double primed of -1 is -7, so this piece tells me that f of x is concave down at x equals -1. Because f prime prime of -1 is negative. This piece tells me f of x has a horizontal tangent line at x equals -1. So I have a horizontal tangent and I'm concave down. So what must be happening there? Well, f primed is 0 and f double primed is negative, so it's got to be a local max, because the only way to have a horizontal tangent line when you are concave down is if you're rolling through a local max. So therefore, by the second derivative test, f of x has a local max at x equals -1. I can't say what that max value is because they haven't told me what f of -1 is. But I do know that the point there has to be a local max because we've got a horizontal tangent and we're concave down. Make sense? Questions about the second derivative test, what this says or how we use it?
Could we see that graph from Desmos again real quick from,
Of course.
thanks.
So really, this is a shifted form of the graph of x cubed minus x. That's all that's going on here. But we've got a local max at -1 because f went from increasing to decreasing there. We used our first derivative test. We've got a local min at 7 because f went from decreasing to increasing there. And then we set f double prime equal to 0, or we found anywhere that f double prime changes sign. So everywhere over here, f double prime was negative, so we knew that we're concave down. And everywhere over here, f double prime is positive, so we know we're concave up. So the point where we changed from being concave down to concave up had to be an inflection point. Okay. Let's see, do I have this up still? Yeah. So I'd like to look at a handful of other examples here. Inflection point, second derivative test. Good, good, good. Okay. This guy we worked with a little bit at the end of class last time. Let's return to him for just a second. I'd like to work numbers 12 and 18 here. Last time with number 18, we found intervals of increase and decrease, and we also found local mins and maxes, but we didn't say anything about the second derivative. And then 12 is also a fun problem. So let's look at both of those and then maybe a trig example. We don't have time. Oh, we don't have time for both of those, do we? All right, so we're just going to return to number 18 then. We'll finish that up. Let's find intervals, I'll copy this down, of increase, decrease, and concave up, down, mins, maxes, and inflection points for f of x equals x to the 4, e to the negative x. All right, so I'm using some shorthand here, inc, dec for increasing, decreasing, and then IP for inflection point. F primed, this is a product rule derivative, is 4x to the 3rd e to the negative x plus x to the 4 times negative e to the negative x, which is e to the negative x times 4x cubed plus x, minus x to the 4, which is x cubed e to the negative x times 4 minus x. So my number line for f primed has two numbers on it. This guy gives me a 0, this guy gives me a 4. And if I test, say, x equals 1 in here, f primed of 1 is 1 times e to the negative 1 times 4 minus 1 is 3. This is positive. And then I will change sign as I hop over each of these according to the multiplicity rule, because this is an odd multiplicity factor at 0. The multiplicity is 3. This is an odd multiplicity factor. So multiplicity 1, the x equals 4. So f is decreasing on the interval -infinity to 0 and 4 to infinity. And f is increasing on the interval 0 to 4. Therefore, by the first derivative test, I have a local, I go from decreasing to increasing at 0. That means I have a local min at x equals 0. And that point is 0, 0. I have a local max at x equals 4, because I go from increasing to decreasing at x equals 4. So i.e. 4 comma, what is that, 64 e to the negative 64? Sorry, 64 e to the negative 4 is a local max. And then if I calculate f double primed of x, I might do that from here, so I can treat it as a simple product rule thing. That would be, I'll differentiate the e to the negative x, that's negative e to the negative x, and leave that alone. That's 4x cubed minus x to the 4. And then I add that to what I get when I leave e to the negative x alone, and I differentiate this. That's going to be 12x squared minus 4x cubed. I can factor the e to the negative x out. And what's left is negative 4x cubed minus x to the 4 plus 12x squared minus 4x cubed. The algebra here is getting a little bit hairy. I'll distribute this negative. I'll leave the e to the negative x alone on the outside. So that's negative 4x cubed plus x to the 4 plus 12x squared minus 4x cubed. Do those cancel? No, they don't, damn. So this is going to be e to the negative x times x to the 4 minus 8x cubed plus 12x squared. And I can factor in x squared out. And what's left is x squared minus 8x plus 12. So this is f double primed. And again, I'm calculating it from f primed. So I'm differentiating this using the product rule. Here I differentiated e to the negative x, and I left the polynomial piece alone. Here I left e to the negative x alone, and I differentiated the polynomial piece. 4x cubed differentiates to 12x squared. Minus x to the 4 differentiates to minus 4x cubed. Coming to this line, I factored e to the negative x out. So this negative is this negative. He stays attached to that first piece. The e to the negative x comes out. and this e to the negative x comes out. So I factored e to the negative x in the second line. In the third line, I took this negative and I distributed it over these parentheses. So the 4x cubed becomes negative 4x cubed. The minus x to the 4 becomes plus x to the 4 because he gets hit by this negative, and negative times negative is positive. Here, I just distributed the positive 1 that's out front here, right? So the parentheses just go away. And then from here to the next line, I combine my like terms. I've got negative 4x cubed minus 4x cubed. That's negative 8x cubed. Plus x to the 4, that's the x to the 4 here, and plus 12x squared, that's this guy. And then I'd like to factor this, if I can. So that's e to the negative x times x squared. And then let's see, does that factor nicely? So I need two numbers that multiply to 12 and sum to negative 8, negative 6 and negative 2. So that's x minus 6, x minus 2. So if I wanted to make a number line for f double primed, this piece gives me a 0, this piece gives me a 6, this piece gives me a 2. So 0, 2, and 6 go on my number line. If I plug in negative 1 over here, if I test x equals negative 1, f primed of negative 1 is e to the 1, negative 1 squared, negative 1 minus 6, negative 1 minus 2. That's e times 1 times negative 7 times negative 3. That's negative 21e. And since e is positive, this is negative. The multiplicity of the factor that gave me this 0, remember that came from this factor, is 2. Since 2 is even, I will not change sign. That's the multiplicity trick. If your number comes from an odd multiplicity factor, you will change sign as you jump over that number. If your number comes from an even multiplicity factor, you will not change sign. So once I knew that this is negative, I can conclude that this must be negative because the even multiplicity tells me you will not change sign. And then both of these other factors are multiplicity 1 factors. Those are odd, so I will change sign as I go over these. So as I go over 2, I go from minus to plus. As I go over 6, I go back from plus to minus. So f is concave down on negative infinity to 0 and 0 to 2. And f is concave up, negative infinity to 0, 0 to 2, and 6 to infinity. And f is concave up on 2 to 6. And then finally, we have inflection points at what x values? Well, at 2, we go from being concave down to concave up. And at 6, we go from being concave up to concave down. 0 is not an inflection point because my concavity didn't change there. I was concave down to the left of 0 and I'm concave down to the right of 0. So 0 is not an inflection point. So that's everything. We found local mins, local maxes, intervals of increase, intervals of decrease, intervals where we're concave down, intervals where we're concave up, and inflection points.
I have a quick question back at the beginning where you had negative e to the negative x, where f prime is fx cubed.
Let's see.
Yeah, top of the page. 4x cubed e to the negative x plus x to the 4. Is that negative e to the negative x? How did you get
It
that?
is. So this is a chain rule derivative. So the whole thing here is a product rule.
Yeah.
But within that product rule, I have a little chain rule. When I go to differentiate this piece, remember the derivative of e to the ax is always a e to the ax. So the derivative of e to the negative 1 times x is negative 1 times e to the negative 1 times x. It's a chain rule thing. So I differentiate the outer function, that's the exponential, and that gives me the e to the negative x back. But then I have to multiply by the derivative of the inside. The derivative of negative x is negative 1.
Oh, shoot. Okay.
So
Thank
it's
you.
a
And
little
then where
chain
did it go?
rule. So from here to here, I factored e to the negative x out.
Yeah.
So this
Oh,
negative is what made this negative.
yeah. Because it
And
multiplied
you see, I
negative 1
messed
by
that up at first too.
4.
Yep, yeah, exactly.
Cool. Thank you.
No problem. Yeah, these calculations, they take some practice. They do. I apologize if I went a little quickly there. So let me zoom this out just a little bit. Give you guys who are writing a second to continue writing. See if I can slide this over and maybe I can even fit. Let's see. Maybe I can even fit this last bit over here. And not quite, not quite. So we'll do it like this. I'll leave this here for now. Yeah, how about like that? There's the derivative calculation and the second derivative calculation. Let's take a look at this graph in Desmos. And let me rescale my y-axis. Let's do it like that. So some interesting stuff is happening here, right? Definitely a local min there, definitely a local max there. And we found those, 0 and 4. So the point 0 comma f of 0, that's the point on the graph associated with x equals 0. That was my local min at x equals 0, 0. At 4 comma f of 4, we had our local max. You can see that I'm concave up everywhere here, and I stay concave up. The fact that f double prime was 0 for a minute at 0, but didn't change sign tells me that we have this flattening down here. But it wasn't an inflection point because everywhere here I'm concave up. On the other hand, I did have an inflection point somewhere here. That was at the point associated with x equals 2. Right? We said 2 is an inflection, is the location of an inflection point because f double prime did change sign there. And we had another inflection point at 6. You see here, we're concave down, but we transition back to being concave up over here. And all of this is consistent with what we said. Decreasing from negative infinity to 0 and from 4 to infinity. Increasing from 0 to 4. Concave up from negative infinity to 0 and 0 to 2. and also from 6 to infinity, concave down from 2 to 4, and we had the local min at 0 and the local max at 4. So this stuff isn't terribly hard as long as you're good at the derivative calculations and the inequality solving. So we need to get comfy with solving these sorts of inequalities. It's not bad, it really isn't. The number line thing, once you get comfortable with it, goes very quickly. But you do need to get comfortable with it, and I especially recommend getting comfortable with that multiplicity trick, because you don't want to have to test a point from every single region. It's nice to just test one point and then fill out the rest of the line using the multiplicity trick. Filling the number line for f prime tells you where you're increasing and decreasing. Filling the line for f double prime tells you where you're concave up and concave down. And that's the majority of your homework this week, right? All of this stuff about second derivative is negative, first derivative is negative. So for number 17, you would want to find a graph that has first derivative negative, so the function should be decreasing, and second derivative negative, so the function should be concave down. So if you are concave down and decreasing, oops, sorry. This is increasing concave up. This is decreasing concave up. This is increasing concave down. This is decreasing concave down. So this would be the one that you wanted here. This is similar to the sort of thing we did at first. They tell you where you've got some critical numbers, where f primed is equal to 0. They say f prime should be positive if x is negative, or if x is between 2 and 4. So horizontal tangent lines at 0, 2, and 4, increasing from negative infinity to 0 and from 2 to 4, decreasing from 0 to 2 and 4 to infinity, concave up between negative 1 and 3, and concave down from negative infinity to 1 and from 3 to infinity. So you just need to very carefully go through each of these and ask which ones have each of these things. So 0, 2, and 4 should be horizontal tangent lines. Okay, well, I've got a horizontal tangent at 0, a horizontal tangent line at 2, but this first graph does not have a horizontal tangent line at 4, so we can rule him out. Horizontal tangent line at 0, horizontal tangent line at 2, horizontal tangent line at 4. So this guy meets the first requirement. The second requirement says f primed is positive, so increasing from negative infinity to 0 and from 2 to 4. This guy is decreasing from negative infinity to 0, not increasing, so you can rule him out. And you'll just go through each of these like that, checking to see which of these graphs satisfies all of these requirements. Look one graph at a time, and then one requirement at a time. And as soon as you find something that doesn't match, you can rule it out. Same sort of shit here, right? They give you the graph of a function. D is clearly a place where f primed is 0. C is a place where f prime should be positive. E is a place where f prime should be negative. And they're asking, where is the first derivative and second derivative positive? So where are you increasing and concave up? Well, at C, I'm increasing, but I'm concave down. At D, I'm neither increasing nor decreasing. At E, I'm decreasing concave down. So definitely none of these. At A, I'm decreasing concave up. So A is no good. At B, I'm increasing, and concave up. So the answer to this first guy would just be B. And then the last few things here, L'Hopital's rule, this is what we're going to talk about on Friday. And this will be the last bit of truly new material for exam 2. So next time we meet, and I'm gonna have to run here now, we're gonna talk about L'Hopital's rule, and then I will send out the study guide. The study guide is all going to come from section 4.5. So there will be some stuff from earlier, but 4.5 doesn't include any new material. It's just asking you to put together all the stuff that we've been doing. So on Friday, I will schedule the exam and send out the study guide. And then we will have our test next Friday, a week from this Friday. So our exam 2 is going to be on the 24th. And it will cover everything that we've done since exam 1. And I'll give a nice thorough explanation of exactly what will be on there. So please get into homework 9. You should be working on this, and you should be able to do everything up to the L'Hopital's rule stuff. And then on Friday, we will talk about L'Hopital's rule. All right, I gotta sign out because I have another class to go teach. I hope that you guys enjoyed today. I'll check the chat here to see if there's anything urgent we need to talk about. Study guide will cover it. Yes, so Krishna asked, the exam will be next Friday. Yes. Study guide will cover 3.4 through 4.5. I think that's correct. It's 3.4 where we left off last time, the chain rule. Yes. So the study guide and exam 2 will be covering from 3.4 up through 4.5. We didn't do 3.11 and we covered only a limited stuff in 3.10. So I'll give you a nice clean breakdown of exactly what will be on the exam and study guide on Friday. All right, I hope you guys have a lovely afternoon. If you need help with anything, you can come by my office hour today or send me an email, Canvas message, and just keep working hard. We're right in the middle of it. This is the hard part. As long as you put in the time now, it'll be okay. So that's it. I'll either see you in my office hour or I'll see you on Friday. Take care, guys.